Hello. So in the previous video, I explained the basic ideas and basic terminology for statistical hypothesis testing with a very simple example of like airline free cancellation policy abusers, right? So the idea is we believe that the customers are all innocent, and then we calculate the distribution of the cancellations, and from there we calculate the ranking of suspiciousness, right? That is, and then we determine how, like from the like we are going to ban the customers from the most suspicious. Then we decide it is our choice whether how much we are going to prevent like deny from the free cancellation policy. So test statistic, null distribution, p-value, significance level, these are the main concepts, like statistical terms that correspond to each of those steps, right? I hope you get the idea. And today I'm going to show you a little more applicable numerical example. And the example with a different example. Now what I have in mind is about your midterm study hours, right? I believe most of the midterm exams are over by now. So I am curious how much students study during the midterm exam, right? So I believe that students spend 30 hours to study for the midterm exams on average. So like average student spends 30 hours. That is my hypothesis, my belief, right? But I'd like to test it. I don't have any evidence why I chose 30 hours. I don't have any answer. I just my feeling. So I surveyed to test my belief. I surveyed 100 random students and asked their midterm study hours. How many hours did you study for the last midterm exams? Based on, like, of course, it's like imaginary survey. I didn't do that actually. But suppose that you did this survey, and surprisingly, I found that the sample mean from the data was 31 hours, which is slightly greater than my belief. My belief was 30, but the data tell me it's 31. So then the problem is, okay, there is a difference of 1 hour. Now my task is, like, there are two choices: to keep my belief or reject my belief. If I'm to keep my belief, that what I'm doing is I will interpret those 1 hour difference as a pure random error, right? So like I did, so as in our previous example, an innocent customer may cancel their reservation for reasonable reasons. So that can happen, right? Random error can happen in the survey. So the 1 hour difference could be just interpreted as a random error. Or if I'm to reject my belief, that means I believe that 31 from the data is a huge difference from my belief 30 hours. 1 hour difference is not ignorable. It cannot be a random error. It's a big difference, too big a difference. So I cannot interpret this as a pure random error. Something is not going well. That's If I take this approach, then I have to uh, reject my hypothesis. So then it depends on the random error, like how big the random error is. And that is related to the standard error again. So we calculate the standard error from the data. That is 10. So from the data, I calculated the mean, I calculated the standard deviation, and we have our belief and we have our sample size. So we have like 30, 100, 31, 10, and additionally we choose 5% significance level. That means I am going to reject the top 5% observation, top 5% most suspicious realization. Then, so that's what I'm going to reject, right? Top 5%. Okay, based on these numbers, let's think about how to build how to build a statistic or test statistic. Okay. And first, my hypothesis will be written in this way. So mu, Greek letter mu, is the expected value of x, where the x is the midterm study hours from a student, for a student, right? And I believe that the average expected value of x is 30. That is my belief. That's the null hypothesis, right? Null hypothesis is mu equals 30. But the alternative hypothesis is mu different from 30. So it's not 30, right? So anything other than 30 is the alternative hypothesis. So I am testing the null hypothesis. We are going to use the sample mean calculated from the data as the test statistic because we know that the sample mean is the best estimator for the population mean, right? We learned this is the best point estimator, so we are going to use this for the same reason, right? The same sample mean is the best single number that that is closest to the unknown population mean, right? Because and then it is simple. The idea is we are going to compare the sample mean calculated from the data and compare that with the belief. My belief about the true mean. I believe the true mean is 30, but the data tell me it's 31. So it's about those difference, okay? And from now on, we have to apply the theory we learned in earlier chapters. We know that X bar is approximately normal. But what you have to pay a little more attention here is we are assuming that the null hypothesis is true. So we still maintain our belief. I believe, still the mean should be 30 hours, right? This assumption is like, I assume that all the customers are innocent. They are not abusing our policy. So that is our starting point in hypothesis testing. We believe that the true mean is 30 hours. And then, okay, then by the central limit theorem, we know that X bar follows normal distribution with the true mean of a single person, single student, comma, this sigma squared is the variance of a single student's study hours divided by the sample size, right? You may remember what it means. And this assumption enters the first parameter, right? Because I believe that the true mean is 30 hours. That implies X bar should be normally distributed around 30 hours, right? So mu is fixed by our null hypothesis. And sample size is given. This is not a problem. But we need to estimate the variance that is already estimated from the data. We estimated the standard deviation from the data, which was 10. So the variance would be 10 squared. So like this, we could recover the sampling distribution. But again, the point here is the mean depends on your belief, right? At this moment, we pretend as if my belief is true. Okay, so if my belief was true, your survey result must be distributed like this, even though it cannot be exactly 30 hours, but your sample average from the survey would be close to 30 and with this much standard deviation. Graphically, this is what it would look like if my belief was true. Okay, so then this is the null distribution of the test statistic if under my null hypothesis, null distribution. So then based on this distribution, so this means if my belief is true, I think it's likely the X bar would be somewhere around 30. But still it is possible that you are going to get like 33 as a result, or like 27 is also possible. Anything is possible, but it becomes unlikely as you go away from your hypothesis, right? So you are going to get like more probability will be close to your hypothesis and less probability outside, right? So we can simply like tell that it is easy to see that this is really unlikely. 20, like say 26 or 34, it is really unlikely based if my hypothesis was true. If my hypothesis was true, 34 is really unlikely. 26 is unlikely. Of course, even smaller numbers or even larger numbers would be unlikely, right? So if I'm to reject the null hypothesis, I have to reject those outside tail outcomes, right? They are the most suspicious outcomes. That means they are the most um, most different from my hypothesis, right? But we observed here, our observation, our observation is realized at this point out of this distribution. So out of this distribution, we happen to see 31. So it's this much likely. How can we then? So we are going to rank. We are going to find our observations, our surveys ranking of suspiciousness here. How can you do that? We are going to calculate the probability from the most suspicious outcome, like most suspicious outcome out the tail. Okay? Then it will be like this. So what outcomes are more suspicious than our observation? Anything outside, anything more like distant from the hypothesis, anything more like further away from 30, which is my hypothesis. So all these outcomes, 32, 33, 34, are more different from my hypothesis. But at the same time, you have to think about this. So I observed 33. How can I compare with, like, for example, 28? They are deviations. They deviate from my hypothesis, but in different directions, right? But 31 is plus 1 from my belief. But 28, for example, 28 is minus 2 from my belief. So even though the direction is the opposite, but the negative side outcomes are also equally suspicious, equally different from the positive side. So we have to think about the negative shocks like equally as the positive shocks. So I will count those outcomes as more suspicious than 31, more different from my hypothesis than what you observe, 31. Okay, so in this case, when you calculate the ranking, as I said, the outside outcomes are most suspicious guys, but there are two directions. You have to treat them equally. Positive side and positive side and negative side are equally unlikely, so ranking is counted, double counted from like both sides. Okay, so this probability, the probability is the area like outside 20 plus minus 1, like 29 and 31. So that area is the probability of more unlikely outcomes. That is the ranking of the suspiciousness of the observation. That's the p-value. Okay, so this is the idea of the p-value, which is not well explained in many statistics courses. So I'd like to give you the basic intuition behind it. Um, it's pretty tricky because, but later calculation is pretty simple, so don't be worried too much. Here is how we calculate it. So as you just saw, we observed 31, but when we count the ranking, we have to think about the other side. So we, of course, anything greater than 31, anything outside 31 is more unlikely, but at the same time, smaller than 29 is as unlikely as greater than 31. So we are going to calculate p-value as the tail probability of both sides, right? Outside of 31 and smaller than 29. And how do we calculate this? We are going to standardize the normal distribution. We know the distribution, so x bar, we calculated the approximate normal distribution parameters like this. So we are going to calculate, use those parameters for the normalization, right? Standardization, I mean. So the mean is 30. The standard deviation of the sample average is the single outcome standard deviation divided by the square root of sample size, right? Right? And you have to do the same thing on all these terms. You have to standardize both x bar and all the counterparts, their counterparts in each tail, on each tail. Okay. And again, another thing I want you to note is 30. Here, 30 is my hypothesis, right? Again, this probability assumes my hypothesis is true, right? So I assume that the true mean is 30 hours, right? So that's why the standardization is based on 30. And then after you calculate this thing, standardized numbers, you get -1 and +1. That is the tail probability on the standard normal distribution outside plus and -1, which is 31.731%. I believe you can do it like on Excel, like calculating the standard normal probability. So this is how we calculate the p-value, okay? And in this process, one thing that we are like it is one thing that it would be useful to define is this standardized value, right? 31 is what you observed, the observed sample mean, and we standardize the sample mean using our hypothesis and the calculated standard deviation and the sample size. We call this as the t-statistic, right? So the name the t-statistic is originated from a statistician in the past who used writing name student, right? He called him student and used t as the t was the his maybe favorite notation. So we still use t as a notation for this standardized test statistic, right? And the interpretation is like this. So 31 is the observed sample mean. 30 is my hypothesis. So the numerator, 31 minus 30 is the difference between the data and my hypothesis. We are standardizing the difference by the sample average, the standard deviation of the sample average, right? Standardize the standardized difference between the data and my belief. That is t-statistic. And of course, if the t-statistic is close to 0, that means the difference will be small. The data and the belief are more consistent. But if t-statistic is further away from 0, that means there is a significant difference between data and your belief. So you are more likely to reject. And then p-value can be calculated based on this t-statistic, right? So we just break down this calculation into step 1 and step 2, okay? So standardization in one step, calculating p-value in another step. So then we can write it this way. So here, because by the way, the t-statistic can be negative or positive. It can take any sign. So we define the p-value using an absolute value. So we have to take, in case t is negative, you may need to denote it as minus absolute value of t, so that it is always minus and it is always positive, because we are just handling two tails. That's the point. We want to have two tails, positive side and the negative side. To make sure it is negative and it is positive, we use the absolute value. But it's pure just technical notation. Okay, so then, okay, anyhow, this is how we calculated the p-value. Then you can conclude that our observation is the ranking of suspiciousness is 31%, which is not that bad, because our cutoff is usually 5%. So I am going to reject the 5% most suspicious outcomes, but mine is below that. So I don't need to reject, right? I will reject only 5%, but it's outside 5%. So I'm not going to reject my null hypothesis. Okay, this is our conclusion. We cannot reject the null hypothesis. Okay, so in the end, we are going to compare the p-value versus the significance level alpha. And if the p-value is greater than alpha, then our interpretation is, oh, our observation is not that suspicious. It's not that unlikely. It's not that different from the hypothesis. So I don't need to change my belief, right? 31 is sufficiently close to, sufficiently consistent with my belief, and the difference is purely random error. Or like a random error of 1 is very much likely, so I don't need to change my mind. Okay, this is how we implement hypothesis testing and how we interpret the results and the terminologies. Okay. So, so then summary, simple summary, we usually consider hypothesis testing about a parameter. And I focused on the population mean. So we usually think about in most cases, in many cases, we have a belief that the true mean equals something. Here, mu0 is a known number. Like I said, it's your belief. So I believe it's 30 hours, then you plug in 30. If you believe it's 100, then mu0 is 100. So this is also your choice, your belief, what you want to test. And its alternative is simply everything else, right? You're betting on anything else. The significance level is another choice of yours, right? And common choice is 5%, but it can be usually 1% or 10%, depending on your preference, the typical choices. And then after you setting your hypothesis and your decision significance, then you observe the data, right? So you first have your belief and then look at the data to see if your belief is consistent or not. And then you calculate the t-statistic and you calculate the p-value. That's how we do the hypothesis testing. Okay? And then this is how we, like after looking at the data, you use the normal approximation. And based on this theory, this is the theoretical justification, theoretical foundation. And especially, I want to re-emphasize the mean is the null hypothesis. You are still believing your hypothesis, right? And then standardize the observed sample mean, and then calculate the p-value. That is how we implement hypothesis testing. So now it is your turn. I slightly change it. I changed the numbers slightly. So then try this. The first question is, first I changed the hypothesis to this. Like say, for the final exam, I believe students spend 50 hours for final exams to prepare for the final exams on average. That is my belief. So I surveyed 100 students, and from the survey, I find that the sample average is 56 hours, and the standard deviation is 20 hours, right? This is what I calculate from 100 observations. From here, find the t-statistic, right? T-statistic for the hypothesis test. And remember, t-statistic is the standardized difference between sample average versus my belief. Okay. And of course, you can peek at the previous slide to see what is the t-statistic. Okay, pause the video now if you need more time. Let me go to the next question. Like you can calculate the t-statistic this way. Sample mean minus your belief. So this is the difference, and you standardize the difference using the standard deviation calculated from the data divided by the sample size, right? So if you do the math, it's 3, right? And then so your like based on your observation, the standardized difference is 3. Then what is the p-value, right? P-value is the probability of more unlikely, more suspicious outcomes. And remember, it is about both tails, both tail probabilities, right? So based on from the standard normal distribution of and compare with 3. Okay, so you will need like a standard normal probability calculator, Excel or online calculator. So try this. This will be more easier than the previous question. Okay, so let me turn to the next one. The answer. The answer is the p-value. So our observed t-statistic is 3. We calculate t-statistic 3. Then the p-value is the probability outside, probability of standard normal distribution outside plus minus 3, plus outside, greater than plus 3 or smaller than minus 3. If you use Excel, then you can find the answer is 0.27%. It's pretty small, right? And now you're suppose that your significance level was 1%. Then in this case, do you reject your hypothesis or not? This is the most important question. When you calculate, when all the things are calculated, can you make the correct decision, correct conclusion or not? Okay, the answer is, so p-value is smaller than 1% significance level. So that means you are going to reject the top most suspicious, most unlike 1% observations. But yours is top 0.2% unlikely, which is extremely unlikely, right? It's extremely outside of the tail, right? So you have to reject the null hypothesis. So back to the numerical example like this. To casually interpret what I just did, I assume that the students study 50 hours on average. The true mean is 50 hours for the final exam. But it is still possible to, like, even if the truth is 50 hours, but still, due to random errors, I may have a sample average of 56 from a survey of 100 students. That is possible. However, it's likely for that to happen, the random error must be really large. And this large, a random error of 6 happens with probability only 0.27%. Very unlikely random error. The random error is too large that it is too unlikely. So this big random error does not happen often. So then, as a result, rather than assuming that my belief is still true, but I would change my belief, and I have to update my hypothesis. So I take the alternative hypothesis rather than my null hypothesis because the data is too inconsistent, too different from my belief. Okay, that is our story, right? So that's what we just saw in our numerical example. Okay, so in the next video, we will continue this work, but there are other ways to make the conclusion. Like so far, I explained the p-value versus significance level. So comparing the p-value and the significance level, but there are other, criteria to reject the null hypothesis. So I will explain 3 different methods in the next video. Yeah, thank you for watching.